Hi, my name is Shourya Mishra, and I have been fascinated since engineering ever since I was a kid. From building Lego cars and planes to building keyboards and robot arms. That same curiosity has led to a love for robotics, mechanical design, and automation. Whether it's creating PCBs from scratch or experimenting with my Lego Rubik's Cube solver, I'm always looking for new ways to challenge myself and bring engineering into my life.
This here is the PCB for EGKey, a custom ergonomic split keyboard that I made. Each half has a 5x4 key layout with two rotary encoders here, and the footprints are arranged to match the natural angle of the hands. The traces run cleanly from each switch through its diode and enter the microcontroller area, keeping the routing tight and efficient. The large red regions are ground pores, which help the signal stability and reduce electrical noise. You can also see it via stitching around the edges, tying the ground layers together for better shielding. The microcontroller sits near the top, with all row and column traces fanning out in an organized way. Power handling and battery connections are grouped close together to keep the power paths short and reliable. Breakaway tabs let the board be manufactured as a single piece and then snapped into left and right halves. The mounting holes are positioned to line up with the case and keep the whole assembly rigid. Overall, the PCB is compact, symmetrical, and optimized for clean routing and easy assembly. Exactly what you want for a custom split keyboard. This here is the right and left side of the case for EGKey. The shape follows the natural angle of a hand, so the outer walls sweep around in a smooth asymmetric contour. The inner wall is lower and straighter, which keeps the thumb area open and comfortable. As you can see, 4 mounting posts on the base. These line up with the PCB standoffs to keep everything rigid and assembled. The perimeter walls differentiate in height, depending on where support is needed, and there is also a clean rectangular cutout on the side and on the back for the USB-C. Everything is modeled with enough clearance for wiring and components, but still tight enough to feel solid in the hand. The left side of the case is identical, just mirrored, so the whole keyboard keeps a consistent ergonomic profile. Together, the two halves form a compact, comfortable shell that fits the EGKey's PCB layout perfectly. Here's the finished keyboard, fully assembled and ready to use. The switches feel crisp and responsive, and the split layout fits naturally under the hands. You can hear how clean the clicks are. The case and PCB keep everything solid with no rattle. The lighting system supports multiple modes, so you can switch from a simple static glow to waves to gradients or reactive lights depending on your mood. Each mode transitions smoothly, and the LEDs stay bright without washing out the keycaps. Overall, EGKey feels great to type on, looks clean on the desk, and brings together all the work from the PCB, case, and firmware into one polished final build. Working on EGKey taught me a lot more than I expected. I learned how to take an idea from a rough sketch all the way to a working product, designing a matrix, writing a PCB, modeling a case, and bringing everything together in firmware. I got better at solving problems step by step, especially when things didn't work the first time. And most importantly, I learned how satisfying it is to build something that's completely on my own. From the electronics to the feel of the final keyboard, this project pushed me, taught me, and made me excited to take on even bigger builds next time. This is my LEGO Mindstorms EV3 Rubik's Cube solving robot. It scans each face using a color sensor in RGB mode, sends that data to a solver algorithm, and then physically rotates the cube to solve it. My biggest challenge came when the robot kept misreading colors under certain lighting. After testing multiple cubes and measuring raw RGB values, I discovered that fluorescent stickers were reflecting the sensor's LED, causing false readings. I implemented a dynamic calibration system that adjusted thresholds based on ambient lighting intensity, and added redundant scan passes for uncertain colors. Eventually, I solved the issue completely by switching to a non-reflective cube. The robot now solves the cube in about 1 minute and 15 seconds. This project taught me that even small variables, light, reflection, sensor delay, can change a system's behavior. It reinforced how mechanical precision and computation accuracy must work together for a design to succeed. Overall, these projects represent how I approach engineering, through curiosity, iteration, and understanding how systems work together. Whether I'm building a keyboard or debugging a sensor on an autonomous system, I enjoy breaking problems down and refining them until they work reliably. Engineering to me is about learning from every failure and using that knowledge to build better designs the next time around. Thank you so much for taking the time to watch and learn about my work.